during B time. All right. Yesterday we kind of dove into this head first. Luckily it was the deep end, so we didn't get hurt. But we'll talk a little bit more about what we talked about and just keep layering stuff on as we go. So if you remember, we had this big hairball, essentially, model of the atom. And it had those weird shapes that would build on each other. Does that sound familiar? Okay, and we said that these shapes, they were sort of spheres. Uh-oh, don't do this to me. All right, there we go. All right, so we had some spheres, and that was like the probable location that you would find an electron based on this new idea of the wave mechanical model. All right, and these spheres, they would get bigger and bigger the more of them you added, because the electrons would repel. And then we had what we call propellers, and they came in groups of 3. You can see these on this worksheet that I handed to you. Well, you picked up technically. You'll see them a little bit better drawn. All right, and I told you that they all come together, but they're groups of 3. So you had your up, down, left, right, and in and out of the board. We were okay with that? All right, and if you remember, each one of these I said could hold a maximum of 2 electrons. Does that sound familiar? Each cloud or sublevel, we're going to call it, could hold 2. All right, but if there were more than 1 in each, then it would be, there's 3 of these, they can each hold 2, so we said that those could account for 6. This could hold 2, but there's 5, so that would account for 10 electrons. And then these can hold 2, but they're in 7 different orientations, so that could really hold 14 electrons. And then right as the bell was starting to ring, I was trying to describe how this model mirrors the periodic table over here. And we'll try that explanation just real quick one more time. The first thing I drew was a circle, and it was a small one, and I said it could hold a maximum of how many electrons? 2. So on the periodic table, there can only be 2 total atoms on the top table because, what's this Snapchat going to turn out to be, Caitlin? Oh, I was be like, this is how cool my science class is. He just scribbles. And so the first one of these could only hold 2, so we said, hey, the top row can only have 2 things, or 2 electrons, or 2 atoms, and that the atom there can have a maximum of 2 electrons. Then I drew another circle that was bigger, but then I drew these right after it. Those circles represent the electrons that lithium and beryllium would have, and then I go over this huge gap, and that was 2 wide, and I come over here. And this is where the propeller type of clouds come in. And so once you get to boron and on, you're going to have the propellers, the up, down, left, right, in and outs. But they can hold a maximum of 6. The way the periodic table works out, these are just groups of 2. If you kind of look at it, if you just look like from a ways away, you might sort of see that there are 1, 2, 3, 4 sections of the periodic table. Can you sort of see that? There's 4 regions of the periodic table. And they match these shapes on the screen. Now they're not circles, but the circle could hold a maximum of how many? 2. So this section of the periodic table is a maximum of 2 wide. Then these could hold how many? 6. So the far right section of the periodic table is 6 atoms wide. And then we get this section right here, which is much, much better drawn right in here. But whatever. They're like 4 lobes instead of 2 that orient themselves in 5 orientations. But they can be 10. So if you notice, this chunk of the periodic table is 10 wide. And then the last section would be down here, and it's 14 wide. Now, this particular periodic table, it's 15 wide, if I remember right. But that's because LA and AC, they actually live right here. They've just taken them out and put them down there. Okay. So the model, these shapes, and the periodic table all sort of go together. Now, let's continue on and hopefully help this to make sense. But there's one thing I want to do on this slide I almost forgot. Instead of saying this is spherical, this is propeller shaped, this is whatever shape, and that is whatever, we don't want to use words. We're going to actually use letters to denote these things. The spherical, this would actually make sense. It's an S. So if you see a sphere, it's an S cloud. And if you look at the periodic table for a second, since this is the one that is 2 wide, meaning 2 across, we call this section of the periodic table the S block. And I think, yeah, you turn this over, you will see on the top that the far left 2 columns are called S. You have 1S, 2S, 3S, 4S, 6S, 5S, and 7. I don't know why I counted that way, but I did. All right? So, if you were there, they're an S. If you have this shape of cloud, they are called P clouds. Or that section on the far right side of the periodic table would be called the P block section of the periodic table, meaning atoms from that part of the periodic table, their electrons are filling the P cloud. All right, these are called the D clouds, and then these are the F clouds. So you can see it real quick. I'll draw it sort of ugly, but whatever. So we have S, not drawn to scale, right? D, P, and F now. And those parts of the periodic table come from our model, even though the periodic table was invented way before the model was. Now, if you look over here, I don't know if I've said this or not. This is the actual real structure of the periodic table. Ignore the missing parts because they've just fallen off and the custodians throw them in the garbage. But you have here, and then the long section on the bottom is cut out normally, like on that one. It really is right here. Then you go here, and then you go there. Okay, the only reason on the periodic table the things are cut out and put in the bottom is to make it fit on a piece of paper a little bit better. I would love to. Oh, that's the wrong button. There you go. You're welcome. Okay. Now, on that little picture, where it had your like 1S, 2S, 3S, where do you think the numbers come from? Go ahead. Not true, but a good guess. Close, but not right either. Yeah, it's the rows. That's all it is. Now, it is actually way more complicated than that. But ultimately, the number in front is just the row we're talking about on the periodic table. Now, here in about a minute, we're going to talk about quantum numbers, and I don't want you to overthink them. In a nutshell, quantum numbers, they tell you the row of the periodic table, okay, which also means the size, essentially. They tell you the shape of the cloud you're filling. So if it would be an S, it would tell you, or it would be a P, it would tell you. And it tells you the orientation that that thing is pointing in. So ultimately, that is all we're going to do. And then, well, there's a fourth one, that's spin. But we'll talk about that. It's whatever, either spins clockwise or counterclockwise. Enough said. Okay, we ready to dive in? If you remember a lot of this, you'll be better off with quantum numbers. All right, I think we already said this, but Schrödinger developed a mathematical treatment in which both the wave and particle nature of matter can be incorporated. It is known as quantum mechanics, and that's our adventure today. Solving the wave equation, which is a really long math equation, gives a set of wave functions, or orbitals, and their corresponding energies. Each orbital describes a spatial distribution of electron density, which is like its likely probability of being found. All right? An orbital is described by a set of 3 quantum numbers. The 3 quantum numbers, if you plug them into the wave function, give you answers. Okay? Or they're the solutions to the wave equation. So, everything I'm going to say is put nicely together on this little worksheet. It's not a worksheet. You don't have to do anything. On this note guide, whatever. I don't usually make these, so here we go. We already did that. Okay, so the very first, there's 4 quantum numbers essentially. The first one is called the principal quantum number, and it is denoted with just the letter N. All right? But don't overthink it. It's just going to be equal to the row of the periodic table we're talking about. It means more than that, but it can also be found that way. The principal quantum number N describes the energy level on which the orbital resides. So we could also say that the periodic table, each row represents an energy level now. Okay? If it's on the first row, it's got the lowest energy. Meaning that the electron lives closest to the nucleus of the atom if we're in the first row. That's what we mean by lowest energy. If it was going to fall into the atom, which it won't, but if it did, it would have the smallest fall, or the lowest energy. You okay with that? Okay. Now, the values of N, and this is important, like really important eventually. This one's easy. They are just any whole number greater than 0. So N could be 1, 2, 3, 4, 5, to infinity, but we're just going to stop at 7. Any guesses why? There's only 7 rows on the periodic table. But I could add energy to an electron, and it could certainly jump much higher than 7. But in this class, we only talk about the ground state of electrons when we're doing this concept. All right. So the values of the quantum number N are 1, 2, 3, to infinity, but really we'll stop at 7. Okay. All right. Now, you don't have to understand this part, but the wave equation is designated with a lowercase psi, which is like that trident symbol. The square of the wave function, psi squared, which if you go into math or science, you'll be sick of that, but whatever, gives a probability density map of where an electron has a statistical certain likelihood of being at any instant in time. Okay, whatever. What that's saying is if we do some math, we can say, hey, we will probably find the electron really close to the center, and it decreases as we go out. We talked about that yesterday. That's math. We don't have to stress about it, but psi squared is where we get these weird shapes, which were spheres, propellers, four-leaf clovers, and whatever you want to call the other thing with a donut in the middle, right? It's math. We don't make them up. It's math. All right. So from this math, we get our second quantum number, which is called the Azimuthal quantum number, or L. In the book and in the notes and anywhere on the internet, L is written in cursive. I don't know why, but it is. Is it on this sheet? I don't know. Who cares? But anyway, you'll see it usually as a cursive L. All right, so this quantum number defines the shape of the orbital. Allowed values of L, they are determined by N. N's going to govern everything, really. The allowed values of L are integers ranging from 0 to n minus 1. We use letter designations to communicate the different values of L and therefore the shapes and types of orbitals. All right, this is a very important thing that you need to put in your notes. We have S, P, D, and F shaped clouds I talked about a second ago, right? These correspond to these azimuthal quantum numbers as follows. An S is designated with a 0 azimuthal quantum number, or L. So L is equal to 0 if we are describing an S cloud. And then it's pretty simple. It just goes 1, 2, 3. Now, this is important because you have to be able to go both from a P to knowing it's a 1 or a 1 to knowing it's a P. We okay with that? Okay. Now, do you remember N was really describing the what on the periodic table? The row on the periodic table. So just real quick, go with me on this little awesome science adventure. If we are talking about the first row of the periodic table, N is equal to 1. Correct? All right, and then L. The allowed values of L are from 0 to n minus 1. What is n minus 1 here? 0. Is there any other allowed value for L? No. So please look at this screen while I say this sentence. In the first row of the periodic table, I can only have one shape, and it is a circle, so it is a sphere. That's not how you spell sphere, but we're going to say it is for right now. So why on the periodic table is there nothing between H and HE? Because I can't have P, D, or F clouds if n is equal to 1. Because L always has to be at minimum 1 less than n. So the top row only has S clouds. Now the second row, look at the periodic table. You can see in the second row, you go way over from here to here, right? These are not drawn to scale. These are my S's. Here's the whatever. This is hideous, but this was n equal 1, right? Now n equals 2 in the second row. So please look. Let me get rid of that embarrassing whatever. If n equals 2, meaning if I'm on the second row of the periodic table, L is the shape of clouds I can have. What are the allowed values of L? 0 and 1. Because remember, L can be any number that is equal to, at minimum, n minus 1, which is 1, going down to 0. So how many allowed shapes are there in the second row? 2. They're there. Now, I'm not going to do the third row because then the world blows up. We'll talk about that later. What's that? I know it is, and it makes me mad too. All right. So far, who's sort of with me right now? All right. Okay. Yes. Say that louder. I'm going deaf. We can still have, like, we don't go past F. And honestly, we don't even know really what F looks like. We can still have them. We just don't know what they look like. All right. So next. Oh, this is a good summary so far. N tells me the row. L tells me the area on the periodic table. Because remember, The periodic table is made out of 4 chunks. S, skinny column. P, far right fat column. D, here. And F at the bottom. So if L equals 3, I have my little chart that tells me I'm talking about what area of the periodic table. I'm in the F. Okay? So the L will tell you the area, the N will tell you the row. Okay. Now, this is just another summary essentially. So in the first row, our L could only be 0, which means we can only have S cloud. In our second row, our N is 2, which means L is 1 or 0. That means I have P and S clouds. In my third row, and I know when you look over there, you're like, that's bullcrap, Davidson, that's the 4th row down. But if you look right here, and we'll explain why it's there. The third row really, when you get to the D, it starts on the 3rd row, even though it's on the 4th row down. Just say okay and still love me. We'll get there. But the answer is because the difference in energy between P and D clouds is so small that when you fill, it goes one way. When you empty, you go the other way. We'll get there. Okay. When N equals 3, L can be 0, 1, or 2, which means I can have S, P, and D clouds. Go ahead. They are. They're the second quantum number. They're the Azimuthal. Now, we have another quantum number. That's the same slide. There we go. The third one is called the magnetic quantum number. And it's listed as ML. The L's lower, like subscript typically. Now this is pretty cool, if it all clicks. ML describes the 3-dimensional orientation of the object. Values are integers ranging from negative L to positive L, including 0. Okay? Therefore, on any given energy level, there can be up to 1s, 3p, 5d, or 7f orbitals. And we'll talk about that right now. I'll leave that up for a second. All right, so what this is saying, let's just look at N equals 1. L would be equal to what? 0. And ML ranges from negative L to positive L, including 0, but it's just 0, right? Are you okay with that? All right. So think about what L equals 0 really means. It's a circle, right? It's a ball. And if you have a ball and you rotate it, does anything about it change? It doesn't. Its orientation doesn't change at all. Yeah, there you go. Okay, so just imagine a ball, no matter its orientation in space, it's still the same orientation. Are we all right with that? Okay, but now when we get to the second row, N equals 2, L can still equal 0, which is just a ball, which only has one orientation in the entire world, right? But it also now has 1, correct? Because L can be equal to this number minus 1. All right? So now, over here, ML, and ignore the 0, it's 1 now. It can range from negative L to positive L. So it can be negative 1, 0, and positive 1. So how many orientations are there? 1, 2, 3 different orientations. You with me? What shape is a 1 denoting? A propeller or a P cloud. And I said, hey, it's a propeller, but there's really how many at a time? 3. 1, 2, 3. I don't know which one denotes which one. I don't really care. So we'll just say up, down, left, right, in and out of the board. Are we okay with that? Okay. When we got to n equals 3, yeah, and where have we heard 5 before? 5D cloud, right? And that's because that's how it is. We'll skip 0 and 1. So now we'll just say, now remember, L could be 0, 1, or 2. We're just going to talk about the 2 now. If L equals 2, then ML is equal to negative 2, negative 1, 0, positive 1, and positive 2. There are 5 different orientations when L equals 2. And that's why we drew 5 4-leaf clovers. The F is negative 3, right? Or sorry, 3. And so it will be negative 3, negative 2, negative 1, 0, and then 1, 2, 3. That's 7 orientations that are allowed due to the quantum numbers and how they work out. Okay. Is that a real thumbs up or a what is going on in my life? All this stuff is right here. Okay? Now, I don't expect this to make perfect sense. I just hope it makes a little sense. And for 2 or 3 of you, I hope you think it's cool. You're like, wow, this is super weird, but it sort of makes sense. All right. Okay, well, you're stuck on 3. For now, can because be a good enough answer? Go ahead. Were we talking 14? Well, it's counting. It's talking about this area right here. It is 14 watt. Is that one 15? Okay. Newman, cover LA and AC with your hands. Okay, because the 2 he's covering with his hands actually fit right there. So when it says 14, it's talking about this F block. Okay. All right. What Isaac is annoyed about and what is annoying, but you just sort of memorize it, is why all of a sudden, if you look at scandium, it's in the 4th row down, but it's a 3D. If you will, look at this little thing right here. If you can memorize this piece right here, you can do any of these problems at all. When you are in S and you are in P, N is N. When you are in D, N is really N minus 1. All right? And it has to do with what we call the Aufbau principle, which is the building up principle. And it has to do with the differences in energy as we add an electron to an atom. When we add an electron to an atom, it takes less energy to add a 4s than it does a 3d. Now that is not explainable 100% as to why. It has to do with its distance, size distance from the nucleus and the size of the cloud. The problem is when we empty them out, they do switch, and it does fit the model better of 3. So it's weird. It doesn't do the same thing going up and down. So for now, they have D's being n minus 1 and F's being n minus 2. So if you can remember, S is n, P is n, D is n minus 1, F is n minus 2, you can do what we're about to do. Now, I've said a lot of words that some of you still probably are like, what is he freaking talking about? It is fine if you don't understand most of this, because you don't have to do most of this. It just helps you understand what we're about to do, which you do have to do. Heather, I don't know if I like that look you just gave me right there. She's like, transfer window closed tomorrow? Oh, just kidding. All right. So this was my attempt probably last year or 2 years ago to draw this model from this quantum mechanics or quantum number idea. All right. What's that? It is magnificent. I like it. All right. This number, 32, this is in the 4th row. It's when we have everything, all their orientations, and knowing each one can hold 2. That's just where it comes from. And it's how wide the periodic table is once we put the F's in. It can be 32 atoms wide. Okay, now, the meat of this, we talked about that. This is what how's that N backwards? That's interesting, but whatever. We'll get to that later. What's that? Yeah, there's a reason for this. Might as well do it now. Yeah, well, I just cloned one and then flipped it. Why is hydrogen diatomic? You don't care? Yeah, you do. Because it's in an S cloud, right? And how many can they hold? 2, but it only has 1. But it wants the second one, right? So what they do is they mix their 2 s orbitals and they overlap. And now if you look, both have 2, right? So that's all that was. This should be way lower, but whatever. All right. They both share 2. How about that? Okay, I don't know where the last... Yeah, for sure. They're super tight until someone better looking comes along. All right, I don't know where the 4th number is on the slides, but it doesn't matter. This is called the magnetic spin number, and it's probably on this. Yeah, it's just the last one. And this one's super easy.
Spin quantum number.
Spin quantum number, wherever that is. This one's very easy because there's no real rule, and you can put either one, and it doesn't matter. The quantum spin number, or of M, oh, come on, Tom. MS, that's your spin, is always equal to plus 1/2 or minus 1/2. And there's no rule to govern that. The only thing that we would say is if we have 2 electrons in the same box, they do not spin the same way. That's the Pauli exclusion principle. So, finally then, we have our 4 quantum numbers. They're on the screen. We have our principal quantum number n, which is equal to 1 to infinity. It describes the row. We have our L. It can be n minus 1 down to 0, and it describes the shape. I guess the other one isn't in here. We had ML, which told me the orientation of the cloud itself, up, down, left, right, in and out, or all the other combinations. All right, and then we finally have the spin, which tells you if it's spinning clockwise or counterclockwise, because an electron literally does spin. All right. Yep, that's right where we're going. When I did this, if you noticed, even though it looked flipped, the arrow represents which way it's spinning. And it doesn't matter if I put a down here and an up there. All that matters is if I put them together, they have to be oppositely spun. No. The up represents clockwise, the down represents counterclockwise. So that the total spin is 0. In a completed shell, the total spin will always equal 0. Okay, now you don't have to know that. So here we go. Quantum numbers, just to wrap it up. If I have a 1, if n equals 1, I need to make this number a what? 0. What would this next number be? 0. And what would this have to be? Plus or minus 1/2. I don't care which one. Either one will be fine. I don't add it. It's positive half or negative half. Nope. You just throw on 1/2 at the end. Are you a positive person? Then you put a negative 1/2 at the end. That's how I roll. Okay. We won't do all of them because it would take all day. But if this is a 2, give me one of the numbers that could go here. 1. Give me one of the numbers that could go here. All right, 0 again. What would this be for Brindley? Negative 1/2. Is this an acceptable set of quantum numbers? Yeah. It hasn't violated anything. What if I put 2, 2, 2, 1/2? Is this allowed? No. Why is this not allowed? That is not at least 1 less than n. I'm going to give you that. I'm going to give you 4 of them and say which one is not an allowed set of quantum numbers. Olivia's ticked. That's all? Pretty much. N, and then L, and then ML, and then MS. No, of L, and it includes 0. So once again, row, location, like general location. This one tells you the orientation in space, and this one tells you the spin. Okay. Two, 1, 1, 1/2. Yes. Yeah. Yeah, ixnay on the okay. All right. What atom might I be talking about here? Any guesses? Beryllium or lithium. How come you knew that? Second row. Oh, no, sorry, you're wrong. It's boron to neon. I didn't look very well. Because if this is 1, that means P. Second row, P. And then this doesn't really tell me anything. It's either upside or up, in and out, whatever. Then it would be Li and Be. And this won't tell you anything either. But these two numbers will give you the rough location of the exact atom we're talking about. Okay. That was a whole lot of stuff. Olivia's fired up because there really isn't hardly any of that on the test. But it helps a ton with electron configurations, which is coming up. It is. Yeah, it does, because you would remember that D's n is -1, which is a pain. I would love to go and slap someone myself, but I can't. Okay, here we go. We talked a lot about this. Oh, there it was. I just went out of order. P's, D's, and energies. So here we go. For a 1-electron hydrogen atom, orbitals on the same energy level have the same energy. That is, they are degenerate. There's not a ton in this next part, so I'm just going fast. But degenerate means they have the same energy. All right? As the number of electrons increases, though, so does the repulsion between them. Therefore, in many electron atoms, orbitals on the same energy level are no longer degenerate, meaning they're no longer the same energy. And remember, when I say energy, we're talking that we've moved it farther away from the nucleus. It's like us. We gain potential energy by moving farther away from the surface of the Earth, right? The electron gains energy as it moves farther from the nucleus. All right? The spin number comes along. All right? The spin of an electron describes its magnetic field, which affects its energy. This isn't really that important. This led to the fourth quantum number, ms. What's that? Yeah. Yeah, exactly. I used the analogy of stairs. Same thing. We jump upstairs. If we fall down them, the amount of energy we lost on the way down will be equal to the energy we put up. Okay. All right, Pauli, you don't need to know these, so that's going to go fast. He says no two electrons in the same atom can have exactly the same energy. For example, no two electrons in the same atom can have identical sets of quantum numbers. They will never, ever be identical. All right, now, there's a lot of this. All of this has led us to electron configurations. And when you learn really how to do these, you're like, you took 35 minutes of my life to make me do this. Well, we wasted some time. Let's be real. All right. Oh, maybe we didn't. Okay. Electron configurations. This is a new language we're going to learn, which is not hard, in my opinion. And I don't think you'll think it's hard either. It's a language that describes how electrons line themselves up when they're around an atom. And they definitely have to do with their quantum numbers, even though we're not really going to use much of what we just did technically, but it helps a ton. Okay, whatever. Electron configurations show a distribution of all electrons in an atom. They consist of a number denoting the energy level. All right? That is also known as N, which means it also shows the row of the periodic table we're talking about. Are you okay with that? Okay, so it shows the number denoting the energy level, or row. Next, it shows a letter denoting the type of orbital. And please remember that the letter corresponded to a quantum number as well, correct? So this is just an example. So we have 4p. That means we're in the fourth row, and we're talking about the p's. You do need to for sure remember, though, when you're in the d's, you're at n-1. When you're in the f's, you're in an n-2. I know that's tricky, but this will come pretty quick. All right? The final thing you'll see in one of these is a superscript number denoting the number of electrons in those orbitals. So now, this thing will tell me the exact location of the atom I'm talking about. What row is it in? Okay, it's in the fourth row. It's filling what shape? All right, the propellers, or that far right side. And this tells me how many over it is. So I'm in 4p, 1, 2, 3, 4, 5. This is describing bromine. Now, we don't typically just write the very end. We write the whole thing. All right? To help us do this, we have what we call orbital diagrams, where we have a box, and then we have a bunch of boxes technically, and they represent an orbital. So, the first orbital we have comes from the first row, because n equals 1, and there's only one orbital in the first row, right? So I have one box, and it's S. But when I go to the second row, I'm now to lithium and beryllium, right? The quantum numbers tell me that that's a 2, but it's still an S, and that can hold 2 electrons, so I put a second box. But then we go across that gap. We're still in the second row, but there were P's, right? How many propellers were there? There was 3. You had chemistry last year. Is it starting to look familiar? All right. And then once we come down here, we're now to the third. So we now have 3, and the first thing you interact with is S, and you would draw a box, and it can hold how many electrons? 2. And then you get to 3p, and you have 3 boxes, and so forth and so on. Now, it gets a little complicated, and we'll get through it. All right. So the Hund rule says for degenerate orbitals, the lowest energy is obtained when the number of electrons with the same spin is maximized. What this is going to tell me, when I have these orbitals, if I have 4 total electrons to put in here, they would first go like this. They'd be separate first, so that 3 of them went there, and then the 4th one would pair up right here. If I only had 2, I'd have 1 here and 1 here. They won't pair until they have to. All right? Now, here's the Tom Davidson version of this process. So you have orbital diagrams with these boxes. These boxes, whoa, did I get in that picture? These boxes correlate to these 2 things very well. And if they don't right now, by tomorrow they for sure will, hopefully. So the first thing you do is you fill from the bottom up. You need to know that no box can have more than 2 electrons in it. And then it's kind of ugly, but it says, I wouldn't even write this way. It says don't pair degenerate boxes until all are half filled. What that means is don't pair on a row until they're half filled. Okay? That's on a row. But you can't go up until all the things lower are filled. So please watch this real fast. We'll stick with blue. Let me make this bigger, actually, I think. Okay, so the way this would fill, and I'll just go all the way, but just watch for a second. And it's hard to draw arrows fast on this, so I'm just putting lines. So 1, 2, I'm full, so I have to go up. 1, 2, I'm full, so I have to go up. 1, 2, 3, I don't pair until I have to. 4, 5, 6. 1, 2. How come right there I didn't go 1 and 1 up here? Because I have to fill before I go up. So 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8. After 4s, what comes knocking? Look at the periodic table. What happens after calcium? You have the D. All right? It's not 4D, though, because remember, when we get to D, it's n minus 1. So, pretend, because this is a pain, but pretend I'm right here. After 4s would be 3D. How many boxes would I put? 5 of them. And if I put 10 electrons in here, they would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm about out of time, so I want to make sure we do something here. Okay, look here. In a nutshell, to write the electron configuration of an atom, you find the number of electrons it has, like nitrogen. Nitrogen has 7 electrons. Then you fill these boxes with 7 lines. 1, 2, 3, 4, 5, 6, 7. And then you write the electron configuration as follows. Please watch. You write these in order and then a superscript number with how many there are. So we have 1s, and how many are in there? 2. 2s, and how many are in there? 2. and then 2p, and how many were in there? 3. And all we've done today led us to that awesome moment right there. All right, let's do, that's the electron configuration for nitrogen. That's going to tell me I'm in the second row in the p area, 3 over, that's nitrogen. No, you write the whole thing. The last thing will tell me where I'm going, but I want the whole thing. Hey, I'm doing one more. I have 30 seconds. If I did Na, it has 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1s2, 2s2, 2p6, 3s1. Okay, I'm going way slower than I planned, but whatevs, we're going to be fine. Okay, please, if you haven't read the section on quantum numbers and electron configurations, please absolutely read this and do the practice problems.
So where it ends?
What?
So is the row that it ends with the section is there?
Yes.